Okay, in the meantime, let me look up the table. And table of chemistry. Okay. And let me go back to sharing my screen. Okay, so let me scroll down here. And I'm looking for the relationship between, what is it, meters and yards, right? Okay. So 1 meter is equal to, write this down before I forget. 1 meter is equal to 1.0936 yards. All right, so that's the relationship that we'll be using. So let me go back to the final exam. So we're converting 12.1 yards to meters, right? So what I would do is start off, of course, with what we're given, which is the 12.1 yards. And I would multiply this by, up here I put 1 meter, down here I put 1.0936 yards. And let's see what that gives. 12.1 divided by 1.0936. So according to my calculation, drawing off the 3 sig figs, the answer is 11.1 meters. And that's basically how that is done. All right, so that's a relatively simple problem. Okay, any questions about this one? Any questions? So let me get this. Let's go down to the next question. Okay, so this one says the density of air at ordinary atmospheric pressure at 25 degrees Celsius is 1.119 grams per liter. What is the mass in kilograms of the air in a room that measures 12.5 by 15.5 by 8.0 feet? All right. So basically, this is involving the relationship between mass, volume, and density. And as we all know, density is equal to mass over volume. Now, what the question is asking for is the mass. So the mass would be equal to density multiplied by the volume. But the thing is that you have to ensure that the units are compatible, because here they give us the units in grams per liter, but they give you the dimensions of the room in feet. Not only that, they're asking also for the mass in kilograms, even though the density is given in grams per liters, right? So to find the mass, what I would do first, and it doesn't matter which one you start off with first, so I'm going to start off with density. The density is 1.19 grams per liter, right? What I would do is convert that to feet cube, because the volume ultimately would have to be expressed in feet cube, right? So we need to go back to the table to see how we go from liters to feet cube. And I think what you can do is go from liters to centimeters cube, and then centimeters cube to feet cube, if I remember correctly. Well, I do know, let me squeeze this here. I know that 1,000 centimeters cube is equal to 1 liter, right? And then I know that 1 inch is equal to 2.54 centimeters. And of course, we all know that 12 inches is equal to 1 foot, right? So this is how we set that pattern, right? I would go from liters to centimeters cube by putting 1 liter here and 1,000 centimeters cube below. And then I would go from centimeters cube to inches cube. Now this part here, you have to be careful. Because you have centimeters cube here, then you're going to have centimeters cube here. And this will be 2.54 centimeters cube, all cube. divided by 1 inch, which would be cubed as well, all right? A very common error that students tend to make when they're doing these types of problems is that they forget to put the cube there, right? And then now, to go from inches cube to feet cube, I'm gonna put 12 inches over 1 foot and all of that cube, all right? So what will happen is that the liters will cancel out, the centimeters cube will cancel out, the inches cube will cancel out, so you'll be left with feet cube down here. But we also need to convert from grams to kilograms, because the question is asking for the mass in kilograms. So what I will do here is that because we have grams right here, I would put 1,000 grams down here. And oh shoot, before I do that, I know I was making an error somewhere. I need to convert, I need to multiply by the volume, which is all of this right here. So let me write that down. I'm going to multiply 12.5 feet times 15.5 feet times 8.0 feet. So basically, this feet cube unit will cancel out these feet cube units here. So basically, you'll be ending up with your answer in grams, which now you have to convert to kilograms. I'm going to continue down here. So you're going to have 1,000 grams down here and 1 kilogram above. And that's the setup, right? Because this gram unit will cancel with that gram unit. So let's see what this gives. 1.19 divided by 1,000 times 2.54 cubed times 12 cubed times 12.5 times 15. Oh shoot. Okay, I need to do this one. Sorry. 0.19 divided by 1,000 times 2.54 cubed times 12 cubed times 12.5 times 15.5 times 8, and then divided by 1.19 divided by 1,000 times 2.54 cubed times 12 cubed times 55 times 5 times 8 divided by. Okay, so according to my calculations, and I need to roll this off to 2 sigfigs. So according to my calculations, this works out to be equal to 52 kilograms of air. That's how that is done. All right. Okay, any questions about this one? Any questions?
No, fraction with the 1 inch in the denominator, what's the number on top?
2.54. 1 inch is equal to 2.54 centimeters. Okay, any other questions about this? Any other questions? Okay, so is it okay for me to clear this? Yes, no, give me some. Let me scroll down to. Oh, okay, so this one is just asking, what is the difference between the molecular formula and the empirical formula for a compound? Can anybody tell me? What's the difference between the molecular formula and the empirical formula for a compound? What? Oh,
What's in empirical?
right, so the empirical formula would be would give you the simplest ratio of the atoms of the different element in a molecule. Right, that's the empirical formula. The empirical formula gives you the simplest ratio of the atoms of the different elements present in a molecule or compound for that matter. All right, and then the molecular formula tells you what? What does the molecular formula tell you? And you guys out there in Zoom, please feel free to chip in. What does the molecular formula tell you?
Like the exact ratio of atoms?
No, not the exact ratio. What do you mean the exact ratio?
Like on some fibers?
Or you mean, okay, well. This is the way I would express it. The molecular formula gives you the actual number of atoms of each element present per molecule, right? So that's it, as far as the molecular formula is concerned. Okay, so empirical formula gives you the simplest ratio of the atoms of the elements in the compound, while the molecular formula gives you the actual number of atoms of each element present per molecule of the compound, right? Okay, so number 5, I'm sorry, the B part is giving you some information about a compound known as histamine. And it gives you information about a sample of histamine, which has a mass of 385 milligrams. And it gives you the breakdown in terms of the masses of the different elements present, carbon, hydrogen, and nitrogen. And it gives you also the molar mass. So the question is asking for the molecular formula. So you guys should know how I like to do things as far as these kind of questions are concerned. I like to construct a table. So in this table, I'm going to have at the top carbon, hydrogen, and nitrogen. And the first row will be the mass of these different elements. Now, in this question, they gave you the actual masses. In other questions, they may give you the percentages, right? And if you remember, way back when we did these kind of problems, we said that we can express those percentages as mass, right? In this row here. So here we're going to record the masses. And for carbon, that's 208 milligrams. For hydrogen, that's 31 milligrams. And for nitrogen, it's 146 milligrams, all right? Then we need to find the moles, right? Now, in this case here, I'm just going to do something here. I'm going to express this in grams. So this will be 0.208 grams. This will be 0.031 grams. And this will be 0.146 grams, right? And the reason why I did that is because to calculate the moles, we need to divide each of these gram values by their respective molar masses. So in the case of carbon, we multiply the 0.208 grams by 1 mole over 12.01 grams. In the case of hydrogen, the 31 milligrams would be multiplied by 1 mole over 1.008 grams. And then finally, in the case of nitrogen, 146 milligrams multiplied by 1 mole over 14.01 grams, all right? So that's how we, oh shoot, I should have done. Let me take that line out. I need to work out each of these. So let's start off with the 0.208 divided by 12.01. And according to my calculation, I got 0.0173 moles, all right? And then in the case of hydrogen, 31, I'm sorry?
Should it be the grams, the 0.031 grams?
No, moles, because,
No, for the hydrogen, nitrogen. For the 31 and the 1.6 milligrams, should it be the grams?
oh, you mean, oh, I'm sorry, my bad, yeah, you're right. Okay, so this should be grams and this should be grams, thank you. Grams, okay, yes. 31 divided by 1.008, and I got 0.033 moles. Okay.
Why is it multiplied by 31? Isn't the 31 in milligrams and the 0.03 milligrams?
Right.
But
And the same is true for this. Okay, thank you. So let me do this again. So 0.031 is what I should have done. Divided by 1.008. So let me erase this here. And this will equal to 0.031 moles, right? And then in the case of 0.146 divided by 14.01, and according to my calculation, this will equal to 0.016 moles, all right? Okay, and what do we do in the next step? Can anybody tell me? Now that we have the moles values calculated, exactly, you divide each of these by the lowest. The lowest number obviously is the 0.0104. So let me just write here, divide by 0.0104 moles. So this will be equal to 1. 0.0173 moles divided by 0.0104 moles be equal to 0.0173 divided by 0.0104. So according to my calculation, this works out to be equal to 1.66. And for the next one, 0.031 divided by 0.0104. And according to this, this will be equal to 0.031 divided by 0.0104 moles. Okay, so according to my calculation, this works out to be equal to when rounded up to 266, 3.0, right? So what would be in the next slide, which I can't fit down here? What I'm going to do is continue above.
Yeah, multiply everything by 2 because 6 is close enough to 10.
Okay, repeat what you just said. I'm sorry.
Multiply everything by 2 because 6 is close enough to 10.
Well, you're partially right. You have to multiply by something, but not 2. Let me continue up here. Because remember the whole idea, you're right about the fact that 1.66 is too far from an integer for you to round up to 2, right? So the question is, what do you multiply 1.66 by to convert it into an integer or a number close to an integer? And the hint lies in the fact that you have 2 6's after the decimal point, 0.66. So what do you think you multiply 1.66 by in order to convert it into an integer? Exactly. So if you multiply by 3, the 1.66 becomes 4.98, which is approximately 5. And 3 times 3 here gives you 9, and 3 times 1 here gives you 3, right? So the empirical formula for this compound is C5H9N, right? But the question is asking for the molecular formula. So what will be the next step? Hint, hint.
I don't remember if it's taken mass of find that one too.
All right, let's take the mass of the empirical formula. In fact, I'm lazy, so I'm just going to have my molar mass calculator do that for me. So the formula is
Should it be N3?
N3, you're right, exactly. Let me put that before I forget. So this should be N3, right? So the empirical formula is C5H9N. And okay, and look at that. So the empirical mass is equal to 111.14 grams per mole. Okay, let me go back to. Okay, so the empirical mass is 111.14 grams per mole. And as you were saying, I think you were saying you divide one by the other, but I think you didn't get it in the right order.
So
It's a molar mass. You calculate the integral factor, which is a molar mass divided by the empirical mass, right? And the molar mass and the empirical mass is approximately equal to 1, right? Or equal to each other. So when you divide the molar mass by the empirical mass, that will be equal to 1. So therefore, the molecular formula is the same as the empirical formula,
how
C5,
do you tell that?
because the empirical mass is 111.14, and the molar mass is 111.
Oh, it gives you that.
Exactly. Yeah, they gave you this, that's a molar mass. So therefore, the molecular formula C5H9N3 will be the same as the empirical formula. And that would be the answer, right? Okay, any questions about this one? Any questions?
Really quickly, say they had given you percentages, like something was like 63%.
Right.
You use that as a mass.
Exactly, right, because what you're doing, when you're doing that, you're assuming that you're working with 100 grams of the substance. So the percentages would be, if it's 100 grams, then the percentages of each element would be the mass in grams per 100 grams. So you can use those numbers in that first line that I showed you earlier. You just put the percentages, but you express it in grams.
60%.
63 grams, and then you convert that to moles, and then you go through, you know, the different steps. Okay, any other questions about this one? Any other questions? Okay, so let me clear this. And let me scroll down to see what's next. Okay, okay, so this is what we were talking about just now, right? They gave you the percentages of the different components in this compound, and they're asking for you to calculate the empirical formula and the molecular formula, and they gave you the molar mass. Okay, so let's do this one. And I want you now to tell me what to write down. So I'm just going to start off by, okay, so we have carbon, hydrogen, nitrogen, and oxygen, right? So carbon, hydrogen, nitrogen, and oxygen. So the first line, as I said before, we just assume 100 grams. So what that means is that the mass of the carbon is 57.14 grams. The hydrogen is 6.16 grams. The nitrogen is 9.52 grams. And the oxygen is 27.18 grams. All right. So what's the next step? Tell me. Okay, so how do we do that for carbon? 57.14 grams. What do we multiply that by?
1 mole.
1 mole over? Nope, 12. 12. Right. And then we do for hydrogen, 6.16 grams multiplied by what? 1 mole over 1.008 grams. In the case of nitrogen, it's 9.52 grams multiplied by what? 1 mole over 14.01 grams. And then in the case of oxygen, 27.18 grams. Oops. Let's see. In the case of oxygen, it's 27.18 grams multiplied by 1 mole over 16.00 grams. Okay, so let's work out each of these. Starting with the carbon. So 57.14 divided by 12.01. And according to my calculation, when rounded off the 4 sig figs, that gives 4.758 moles. In the case of hydrogen, 6.16 divided by 1.008. And according to my calculation, this gives 6.11 when rounded off to 3 sig figs. And then in the case of nitrogen, 9.52 divided by 14.01. And according to my calculation, this works out to be equal to 0.680 moles. And then finally, in the case of oxygen, it's 27.18 divided by 16. And I got 466, so 1.699 moles. All right, okay. Next step.
0.680.
Exactly, that's the lowest of these. So divide right through by 0.680 moles. This will give 1. So let me divide 4.758 moles by 0.680 moles. So 4.758 divided by 0.680. And according to my calculation, rounded off to 3 sig figs, that would be 7.00. And then 6.11 divided by sorry, 6.11 divided by 0.680. And according to my calculation, this gives, we run it off the 366, 8.99. And then over here for oxygen, I'm dividing 1.699 by 0.680. And according to my calculation, this gives, when rounded off to the 4 sig figs, 2.499. Okay, so what do we do after this? Let me erase this here. Since I need more space. Okay, so what is the next step in this process? And the reason why is because this here is too far from any integer to round off up to whatever. So we multiply this line right through by 2. So 2 times 7.00 gives you 14.00. 2 times 8.99. 17.98. And this will give you 2, and this will give you 4.998. So now we have some numbers that are close to integers. So this will equal to 14. This can be approximated to be equal to 18, that's 2. And this can be approximated to be equal to 5. So the empirical formula is C14, H18, N2, O5. But we're not finished yet, because the question is asking not only for the empirical formula, it's asking for the molecular formula, and we're going to use this. So how do we get from the empirical formula, to the molecular formula? Okay, so let me, again, with my laser self, use my trusty molar mass calculator. 2, 5. Let's see what this gives. So, according to this, the empirical mass is equal to 294.30 grams per mole. So again, go back to this here. So again, the empirical mass is equal to the molar mass, right? So basically what that means is that the molecular formula is the same thing. C14, H18, N2, O5. So again, the molar mass, the empirical formula and the molecular formula are both one and the same. Okay. And let me just say, I can guarantee that in your final exam, there'll be a question like this. All right, so.
Are you sure there's only 9?
What's that?
Are you sure?
If we did 9 chapters, yeah. But this will definitely be at least one of the questions that you're going to get. I'm sorry? Exactly. Percent composition and 4 masses given, and you're actually calculating empirical and or the molecular form. Okay, any questions about this one? Any questions? Any questions out there in Zoom? Any questions? Okay, I take it it's okay for me to clear this, so let me do that now. And let me do that, let me just go down. Okay, this one is asking how would you prepare 325 mils of a 0.150 M solution of sucrose? And it gives you the formula for sucrose. So again, we did one experiment in the lab which deals with something like this, where you're making a solution from scratch, from the solute and the solvent, and you're going to make a solution of a specific concentration. So the way you go about this is that you have to do the calculation first, and then you're going to describe what you're going to do in practice. So basically, what I would do is start off with the 325 mils convert that to liters, 1 liter over 1,000 mils, and then multiply that by the molarity, which is 0.150 moles over 1 liter, and then I'll convert that to grams, which means that we have to determine the molar mass of the sucrose. So let me do that here. So the formula of sucrose is C22 Oh no, hold on, what's the formula?
C12.
C12, what did I say, C12? C12, H22O11, right? Okay, so 342.30 grams per mole. 342.30 grams per 1 mole, right? So, okay, so, all right, so that's the setup. So 325 divided by 1,000 times 0.15 times 342.30. And according to my calculation, this works out to be equal to, when rounded off 3 sig figs, 16.7 grams, right? So that's the calculation part in response to the question. Now, you need to make a statement because the question is asking for you to describe how you make a solution. So what I would say is a short statement, nothing complicated. I would say weigh 16.7 grams of the sucrose and add water to make a final volume of 325 mils. And that's it. All right. That's basically how you would do that. Okay. Now, an incorrect answer would be you measure 325 mils of water added to the sucrose, right? That's incorrect. And the reason why is because in practice, there's no guarantee that the final volume, if you do it that way, would be 325, right? So please make a note of that. You add water until the final volume of the solution is 325 mils. Okay. Any question about this? Any questions? Questions? Okay, let me clear this. And let me move on to B. So B says, what minimum number of grams of oxalic acid, monohydrate, and it gives you the formula here, will you specify for titration of no fewer than 15.0 mils of a 0.100 m solution of sodium hydroxide? And it says here, both the hydrogens from the oxalic acid are replaceable in this reaction. So the way I'd go about this first is that I'll write first a balanced equation for this reaction. And the reaction is between the oxalic acid and the sodium hydroxide. And because these two hydrogens will be replaced, then you're going to end up with Na2C2O4 plus H2O. And then you have to balance it. And to balance it, I will put a 2 here, and I will put a 2 here, and that's it, right? That's a balanced equation. So you have to first start off with your balanced equation, and then now what I will do is start off with the 15.0 mils of the sodium hydroxide solution. I will convert that to liters, 1 liter of NaOH over 1,000 mils of NaOH. Oops. NaOH, and then I'll look at the mole ratio between the sodium hydroxide and the oxalic acid. That's a 2-to-1 mole ratio. Oh no, before we do that, actually, I would multiply by the molarity first. 0.100 moles of sodium hydroxide over 1 liter, right? Then we do the mole ratio. So far, this will cancel out with this. This will cancel out with this. And then the mole ratio comes in. again, 2-to-1 mole ratio. I'm gonna put 1 mole of the oxalic acid above as the numerator, and 2 moles of sodium hydroxide below as the denominator, right? So that this will go with that, all right? And then the next step would be to convert from moles of oxalic acid to grams. So again, you're gonna need your molar mass. And again, I'm going to go to my molar mass calculator here. So for oxalic acid, H2C2O4.
You also adding the water. Since-
Oh yes, you need to add the water, thank you. H2 O.
You're writing out the equation, do we add that water in?
It's not necessary, because, well, let me do this first. Well, according to this, the molar mass is 126.7. 126. 1.7 grams of oxalic acid. Come on. Okay, so to answer your question, Miss Spall, okay, to answer your question, it's not necessary because if you include the 2 water molecules here, right? Then you're gonna end up with 4 water molecules here. It doesn't change the stoichiometry between the oxalic acid and the sodium hydroxide, so it's not that important. Okay, so let's do the calculation here. 15 divided by 1000 times 0.1 divided by 2 times 126.07. Oh, I did that wrong. 15 divided by 1000 times 0.1 divided by 2 times 126.07. Okay, so according to my calculation, this works out to be equal to, when we round it out to 3 sig figs, 0.0946. And that's basically half oxalic acid, H2C2O4 dot 2H2. And I should have included dot 2H2 here. All right, so that's basically how that is done. All right.
You, when calculating like final mass, did you add the H2 or just one H2?
No, it should be 2H2. 2H2O here and here. That's important for us to get in this number here, which is the molar mass of the, and this should be 2H2 here as well. Well, this should be 2H2 as well, if you're including the 2H2 here in this equation right here. But the important thing is that you take those 2 water molecules into account when you're calculating the molar mass of the oxalic acid. That's the important thing right here. I'm sorry? For the oxalic acid? Oh, it's what?
Yeah.
Okay, thank you very much for correcting me on that. I don't know where I went into this 2 water molecules, so this should be 1 water molecule here. That means that the molar mass of water of the compound is wrong. So let me go back to erasing this here. And let me go back to my trusty molar mass calculator. So, so this should be 1 water molecule. So it should be 108.45. So this should be 108.05 grams. So I need to redo that calculation. Okay, so let me redo this. 15 divided by 1000 times 0.1 divided by 2 times 108.05, and that is equal to, according to my calculations, 0.0810. 0.0810 grams of oxalic acid, monohydrate. Okay, any question about this? Any questions? Okay, so I take it I can clear this. Let's scroll on further to see what's in store. Oh, okay, so this question says state Graham's law of diffusion. Can anybody tell me in your own words, what is Graham's law of diffusion? And that includes you guys out there in Zoom. Feel free to chip in. What is Graham's law of effusion?
You know, there's gonna be any like state questions like this.
I don't know yet. I haven't put it together yet, but yeah, you may get 1 or 2 questions where you're asked to state something or define something, but most of the questions will be calculations, pretty much. But you might be asked, for example, Boyle's law, Charles' law, you know, what else did you know, or you may be asked to explain something, like why is it, according to the kinetic molecular theory, why is it that when you reduce the volume of the gas, the pressure increases? Right? So, Graham's law of diffusion. Nobody knows? Write this down. Graham's law of diffusion says the rate of diffusion of a gas is inversely proportional to the square root of its molar mass. Is inversely proportional to the square root of the molar mass at a constant temperature and pressure. Rate of diffusion of a gas is inversely proportional to the square root of the molar mass at a constant temperature and pressure. One way of expressing it mathematically is this right here. Rate is proportional to 1 over the square root of molar mass at constant temperature and pressure, right? Okay, so basically what this law is telling you is that the heavier the gas molecule, the slower will be the rate of diffusion, provided that the temperature and pressure is constant, right? And that is key to answering the B part. The B part says, place the following gases in order of increasing average molecular speeds at 300 Kelvin, right? And it gives you 1, 2, 3, 4, 5 different gases, right? Now, it says you're going to place them in order of increasing average molecular speeds. So what that means is basically you're going to start from the slowest to the fastest, right? So, how would you determine that order based on Graham's law of diffusion? What would be the first thing you do in order to answer this question? There you go. So you'd have to go and find the molar masses of all these gases here. Now I know that for carbon dioxide it's 44.01. For N2O5, again, so N2O5. Okay, 108.01. Okay, so 108.01 for hydrogen fluoride. I know fluorine is 19, so I would say 19. I'm sorry, 19 plus 1.01. So I would say 20.01. Fluorine is 2 times 19, so that's 38.00. And helium is 4.003. Okay, so now that we have the molar masses, then what? Remember, we're starting from the slowest to the fastest. So of these, which would be the slowest? Sure about that? Remember, the heavier molecules are the one that would move the slowest. So which one has the highest molar mass here? The 205. So that would be the slowest, followed by A205, I'm sorry. Followed by CO2, followed by F2, followed by HF, and then helium will be the fastest. All right? And let me just tell you, I've seen in the past where there's this formula that you need to, I don't remember if this is given in the packet, but there's this formula for calculating the actual rate. Rate is equal to the square root of 3RT over M, right? So this is how, like, if you're given the molar mass of one particular compound, gaseous molecule, this is how you calculate the rate of diffusion. But what I've seen some students do when they're given questions of this type, instead of doing like what we just did, just look at the molar masses and then put them in order, students went through the trouble of calculating the rate in each case, which is not necessary. You see what I'm saying? So if you're given like a series of molecules, you don't need to use that formula. You just look at your molar masses and you order them according to your molar masses. If you're asked to calculate the rate of diffusion, then this would be the formula that you would use. In fact, I think, if I'm not mistaken, below, they were actually asking for that. Well, before I scroll down, are you finished with this? Can I, okay, let me clear all this. And I think, if I'm not mistaken, there's a question where they actually ask you, okay, here it is. Okay, so in this question, they're asking for you to calculate the root mean square speeds of these two gases, right, at 300 Kelvin. That's where this formula would come in. So the formula is, as I said before, the root mean square speed is equal to the square root of 3RT over M. And let me just say something, again, this is another common error that students tend to make. R, in this case, is equal to 8.31 joules per mole Kelvin. That's the value of R you're going to use in this equation. And the M here is the molar mass. Normally, the molar mass will be expressed in grams per mole. But in this case, you need to express it in kilograms per mole, which means that whatever the molar mass is in grams per mole, you have to divide by 1,000, and then you plug it into that equation to get the answer. So in this case, they're asking for the root mean squared speed for CO. That would be equal to the square root of 3 times 8.31 joules per mole Kelvin. Sorry, folks. I don't know why this is not being itself. Okay. Joules per mole Kelvin times the temperature, which is 300 Kelvin. All right. And then we divide that by the molar mass. Now, the molar mass of carbon monoxide is 12.01 plus 16. So that's 28.01 grams per mole, but you have to convert that to kilograms per mole. So you're going to have 1 kilogram here, 1,000 grams here, and that's how you do that, right? So let's do the number crunching. 3 times 3.81. I'm sorry, 8.31. 3 times 8.1 times 300 divided by 28.01 divided by 1,000. And then I find the square root of all of that. And according to my calculations, and please correct me if I'm wrong, but according to my calculations, when I rounded out to 3 sig figs, the answer is 517 meters per second. And that's how you do that. And that's for carbon monoxide. And basically you do the same thing for helium. The only difference is that you're going to use a different molar mass for helium down here. But the setup is basically the same.
Is this formula in the package or just like?
Good question. I think,
And then constant.
let me see. Okay, should be here. Can I clear all this? Okay, so.
It's still a formula that's not in the package to answer a question. Are we allowed to ask you? I mean.
You can ask, but I'll probably tell you no. Well, okay, so let's see, should be, okay, here it is. That's a root mean squared equation. Right here. I see it gives you some others, but it doesn't give you everything.
And then I think, I'm pretty sure that it defines the constants. That's nice.
Oh, you mean like,
Like the R.
actually, you'll be given this page as well, which has a fundamental constant. So let me see if R is there. R should be there. Okay, it gives you both this value of R and this value of R. So that would be included in the handout, which I'll give you guys along with the test. Excuse me. Okay, so let me go back to the final exam. All right, so this question is a gas stoichiometry type question. And it says a sample, it gives you the mass of a sample of calcium carbide, reacts with water to produce acetylene gas and aqueous calcium hydroxide. If the acetylene gas is collected over water at 17 degrees and 740.0 millimeters mercury, how many mils of the acetylene gas were produced? And it gives you that at 17 degrees Celsius, the vapor pressure of water is 14.5 millimeters mercury. Okay, so this is what I would do. I would first start out with a balanced equation. So you have to read the question in order to get information so that you can get an equation. And calcium carbide is one reactant, and it's reacting with water to produce acetylene gas, C2H2, and calcium hydroxide, CaOH, and it gives you the two here. And of course, you have to balance it. So how do we balance it? Let's see here. You have one calcium on both sides. You have two carbons, you have two hydrogens. You have four hydrogens on this side, so I'll put a two here. And two oxygens. So now I think the equation is balanced, all right? Okay. So it says that you have 3.25 grams of calcium carbide. You have to convert that to moles. So you have 1 mole of calcium carbide. Over the molar mass, so again, I'm going to go to my calculator here. CaC2. So according to this, the molar mass is 64.10 grams of calcium carbide. Okay, and then now we look at the mole ratio. We go back to the exam. Okay, so the next step would be the mole ratio between the calcium carbide and acetylene, right? And that's a 1-to-1 mole ratio. So we're going to put 1 mole of C2H2 here above, 1 mole of calcium carbide below. And then the next step is, well, that's it actually, as far as the setup is concerned. So let me erase this here and do this calculation here. So 3.25 divided by 64.10 and multiply by 1. So according to my calculation, this works out to be 0.0507. And this would be moles of calcium carbide, right? Now, what the question is asking for is the volume of the acetylene, right? We have the moles here, and to calculate the volume, the formula that we're going to use is PV is equal to nRT. You have to rearrange this to get V, which is nRT over P. Now here's the thing. Let me see here. We know what the number of moles is, that's N. The temperature is given, which is 17 degrees, which we have to convert to Kelvin. And R is, of course, 0.0826 liters atmospheres over mole Kelvin, right? The only thing that's a bit of a mystery is the pressure, right? Now, the pressure that is given here is the pressure of the combination of the gas and the water vapor, because remember the question says that the gas is collected over water, right? So when you collect gas over water, that mixture will not only be the gas itself that you're collecting, but water vapor as well. Now, the key to finding out the pressure of the gas itself is the fact that the vapor pressure of water is given here at the same temperature. So I'm just going to squeeze it right here, that the pressure of the acetylene, C2H2, will be equal to the total vapor pressure of the mixture of okay, let me rewrite this here. The total pressure of the mixture is equal to the vapor pressure plus the pressure of the acetylene, right? So the pressure of the acetylene will be equal to the total pressure minus the vapor pressure of water. They gave you the total pressure here, which is 740.0 millimeters of mercury. And you're going to minus from that the vapor pressure of water, which is 14.5 millimeters of mercury. So when you do that, you're going to end up with 740 minus 14.5, 740 minus 14.5. And according to my calculation, this works out to equal to 725.5 millimeters of mercury, right? So that would be the pressure that you're going to put down here. So let's put everything into this equation to solve for the volume. 0.0507 moles multiplied by R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 17 degrees, which we have to convert to Kelvin. So 17 plus 273 equals to 290 Kelvin. And then we divide all of that by the pressure that we just calculated here. But there's another thing that we need to do to this. And that is that we need to convert this to atmospheres. So we're going to multiply that by 1 atmosphere over 760 millimeters mercury. And that would be the complete setup for you to calculate the volume. In terms of unit cancellations that will occur, the moles will cancel out here and here, the kelvins will cancel out here and here, millimeters mercury will cancel out here and here, atmospheres will cancel out here and here. So the only unit remaining would be the liter unit. So let me just do the number crunching now. 0.0507 times 0.0821 times 290, and then divide that by 725.5 divided by 760, and then according to my calculations, rounded off the 3 sig figs, the final answer would be 1.26 liters. And that's how that is done. All right. Okay, any questions about this one? Any questions? Any questions? Any questions out there in Zoom? Okay, what time is it? Oh, only 5 minutes left. Okay, I take it I can clear this. Let me clear this, and let me see what the next question is. Oh, do we? Okay, I'm not sure if we have time to complete this, but I'm gonna at least get a start on this. Okay, so this question, it says you're mixing two substances, silver nitrate and hydrochloric acid, and you're gonna get a white precipitate form, which will be the silver chloride. The solution is filtered, and the precipitate collected and dried, and the dried precipitate is measured to have a mass of 23.6 grams. What is the theoretical and percent yield? All right, so this is a combination of stoichiometry, limit and reactants, and percent yield and all that good stuff, right? So what's the first thing that you need to do in order to answer this question? Okay, so what would be the equation? What are the reactants? Let's start off with that first.
Silver nitrate.
Silver nitrate, okay, and,
Hydrochloric acid.
okay. And they gave you one of the products, but they should be able to figure out the other product. So what's the product that they gave you directly? Silver chloride. So what do you think the other product is?
And hydrogen and nitrate, that just makes it.
Nitric acid, exactly. And fortunately for us, this equation is already balanced, right? So we don't need to make any changes as far as the coefficients are concerned. So the next step would be to find out which is the limiting reactant. So to do that, we start off with the 50 grams of the silver nitrate. We have to convert that to moles. So 1 mole of AgNO3. And down here, we're gonna get the molar mass. So again, let me do the calculation with my 169.87. So that goes here, 169.87 grams of AgNO3. And then the next conversion factor is the mole ratio between the silver chloride, let's get back to. Right, the next conversion factor will be the mole ratio between the silver chloride and the silver nitrate, so that's 1 to 1, 1 mole AgCl, 1 mole AgNO3. And we do that calculation, so that's 50 divided by 169.87. And that gives 0.294 moles of AgCl, right? Then we do the same thing or similar thing with the 50 grams of HCl. We convert that to moles, 1 mole of HCl. Now in the case of HCl, chlorine is 35.45 plus 1.688. So the molar mass of HCl is 36.46 grams of HCl. And then we look at the mole ratio between the silver chloride and HCl, and again, it's 1 to 1. So 50 divided by 36.46. And then according to my calculation, this works out to be 1.37 moles of AgCl, right? So based on these two calculated values here, this is low, which means that this is a limiting reactant, right? And this would be the excess reactant, right? But the question is asking for the theoretical yield. So what we need to do is to find the theoretical yield. We take the mole value here for the lowest one, 0.294 moles, and we multiply that by the molar mass. So 1 mole of silver chloride, and the molar mass of silver chloride, again, I would have to go to my calculator for that. So in the case of silver chloride, molar mass is 143. 143.32. Okay. So let's see what that gives, 0.294 times 143.32. And according to my calculation, this works out to be equal to 42.1 grams.
So that's maybe 1.336.
I'm sorry?
For the theoretical on the top, it's asking 1.36.
No, this should be 3.2.
32.
Let me check and make sure, but I'm quite sure it's 3.2. Yeah, 143.32. Okay, so let's see here. So according to my calculation, when I do the multiplication, that gives 42.1 grams. That would be the theoretical yield, and then the percent yield would be the actual yield divided by the theoretical yield times 100%. So the actual yield is this right here, 23.6 grams divided by the theoretical yield, which is 42.1 grams times 100%. And let's see what that gives, 23.6 divided by 42.1 times 100. And according to my calculation, this works out to be 56.1%. And that's how that is done.
So you said you want to make yourself available as a right?
Okay, yes, in fact, I was scribbling down some dates to see when I can make myself available. I'll definitely be in my office today from 1 to 4. And I have some tentative dates here. Let me, and I'm going to post this in Canvas as well. Let me clear this here. And bring this calendar up here. Okay, so I have some tentative dates here. May 4th, which is what day? May 4th is. Oh, that's Sunday, right? So I was thinking that I'll make myself available on Skype on May 4th from 1 to 6. And okay, so on Monday I'll be at the color, available from 2 to 6. And then on Tuesday I'll be here from 9 to 4. Now I just remember that Skype will no longer be in operation starting May 5th, so I may have to make some alternative arrangements, maybe Zoom.
June Tuesday.
Huh?
May.
When I'm here, if you want to talk to me online, I think we'd have to do it by Zoom because Skype is closing down their operations. They're converting to Team or something like that, which I
So
need
you'll
to.
be here Tuesday?
I'll be here on Tuesday of next week. I'll be at the color on Monday. We're here on Tuesday, from 9 to 4.
You have an answer key to this?
Let
That's the answer, solving for the answers, no.
me see. Let me go back to files. To the final exam, right? And this was for spring 23. So let me see if I have the answer key for that. No, that's not it. Okay, I don't think I'm let's check this one. Yeah, I don't think I have the final, I mean, for that final, I don't think I have the answer key for that. I could try to put it together if I have the time,
Just come to your office hours.
or you can go to office hours, yeah. Alrighty. Okay, and for you guys out there in Zoom, I'm signing off.